Hi everyone. Today we're going to study Kirchhoff's theorem. Kirchhoff's theorem is also known as matrix tree theorem. Let capital M be the matrix obtained from the adjacency matrix of a connected graph G by changing all 1 to -1 and replacing each diagonal 0 by the degree of the corresponding vertex. Then, the number of spanning trees of G is equal to the value of any cofactor of M. Example 1. Find the number of spanning trees of the graph G. This is our graph. First, we're going to write the adjacency matrix of G. And here it is, the matrix A of the graph G. So for the first element, we write 0. This is for AA. There is no loop for the A. That's why this is 0. Next, AB, we write here 1. There is an edge connecting AB. Next, AC, we write here 0. There is no edge connecting A and C. Next, for AD, we write here 1 because there is an edge connecting A and D, so on and so forth. Then, by Kirchhoff's theorem, what we will do is we will change all 1 by -1. Also, on the diagonal, we can see here that all are zeros. We're going to change this diagonal with zeros by the degree of corresponding vertex. So we have this matrix M. All 1 here are changed into -1. Look at the diagonal. The first 0 here in the diagonal corresponds to the degree of A. So we write here 2. The 0 here, the degree of B, so we write 3. The 0 in here means the degree for C, and we write here 2. And we write here 3 for the degree of vertex D. After we derive the matrix M, we will compute for any cofactor. Let's say at 1, 1. It means we will have this matrix. So we're going to expand by first row. It will be like this. 3 times the matrix 2, -1, -1, 3 minus the -1 times the matrix -1, -1, -1, 3 plus -1 times the matrix -1, 2, -1, -1. Evaluating this, we will have this 3 times the quantity 6 minus 1 plus the quantity -3 minus 1 plus -1 times the quantity 1 plus 2. Now let us simplify further. The 6 minus 1 is 5 times 3 is 15. -3 minus 1 is -4. -1 times 1 plus 2, we will have -3. Then the final answer is 8. It means there are 8 spanning trees for the graph G. We're going to draw the spanning trees of this graph on the next problem. Example 2. How many non-isomorphic spanning trees does graph G has? This graph G is the same graph from example 1. From example 1, we're able to solve that there are 8 spanning trees of the graph. And here are the spanning trees. Note that when two simple graphs are isomorphic, there is a 1-to-1 correspondence between vertices of the two graphs that preserves the adjacency relationship. Two simple graphs that are not isomorphic are called non-isomorphic. We can see that the graph 1 and 6 are isomorphic. Also, graphs 2, 3, 4, 5, 7, and 8 are isomorphic. Hence, there are only two non-isomorphic spanning trees of the given graph.